All right, let's dive right in. We are looking at a huge breakthrough in how we understand the very building blocks of life and medicine. We're talking about finding a smarter, much faster way to simulate these massive molecules that are so critical to our health, everything from everyday proteins to the next generation of life-saving drugs. So, you gotta ask, right? Why is this so incredibly hard? Well, a huge part of the answer is this massive computational problem that, honestly, has pushed even our best supercomputers to their absolute limits. See, to design a drug, you first have to understand its target, usually a giant, complex protein, with perfect accuracy. And that's where things get really, really tricky. Just look at this number for a second. 2,418. What is that? That's the number of molecular orbitals you have to deal with just to simulate a single insulin molecule. And that's just at a basic level. Trying to calculate how every single one of those interacts with every other one, well, that's just a monumental task. It's such a big deal. It's been called a grand challenge of modern science. And that really gets to the heart of this molecular simulation problem. We need to understand these molecules with quantum level precision to make real progress in things like drug design. But the sheer scale of it all is, well, it's just overwhelming. So here's the bottom line. For all their amazing power, our current classical supercomputers just can't handle these giants head on. They hit a computational wall. And this forces scientists to use approximations, which can end up sacrificing the very accuracy they're looking for. It's kind of like trying to build a perfect scale model using blurry instructions. Okay, so if you can't solve the whole massive puzzle at once, what do? Well, you get smarter. The answer lies in a really elegant and powerful strategy: divide and conquer. So what these researchers did was pretty clever. They used this divide and conquer strategy called density matrix embedding theory, or DMET for short. The core idea is actually pretty simple. Instead of trying to calculate everything about a huge molecule at once, you break it down. You intelligently slice off the most important active part from its surrounding environment. Now, this is where it gets really interesting. The old way was just brute force. You try to simulate the entire thing in the highest detail possible, which, for big molecules, is pretty much impossible. This new, focused method is so much smarter. It pours all of the computational horsepower into that small, critical region, the active site, while treating the rest of the molecule with an easier, less demanding calculation. Think of it like rendering a movie. You focus all your processing power on the main character, not the trees in the background. But, and this is a big but, to handle that super accurate calculation on the most important part, the researchers brought in a powerful new player. And this is where things get really exciting, because it brings quantum computers into the picture. They used a quantum method called sample-based quantum diagonalization, or SQD. The best way to think about it is like creating a hybrid dream team. The quantum computer isn't asked to solve the whole problem by itself. Nope. Its job is to intelligently sample the most likely answers, basically giving the classical computer a massive head start by pointing it exactly in the right direction. So this isn't about replacing classical computers. Not at all. It's about synergy. The quantum processor does what it does best, exploring this vast space of possibilities to carve out a smaller, more focused version of the problem. Then its classical partner steps in to efficiently solve that simplified puzzle. You're really getting the best of both worlds. A great strategy is one thing, but you have to ask, does it actually work in the real world? So the researchers put this combined DMET-SQD method to the test on some seriously challenging molecules. And wow, this slide really shows you the payoff. For a molecule called cyclohexane, a full simulation would take 89 qubits. But by using that DME divide and conquer approach, they shrunk the problem down to a much more manageable 32-qubit simulation. That is a huge reduction, and it makes it actually feasible to run on the quantum hardware we have today. So for their first test, they went with a classic, a ring of 18 hydrogen atoms. This is a standard benchmark problem in the field. It's like a standardized exam for quantum algorithms to see how new methods stack up against the very best, highly accurate calculations we already have. And the results? They were just impressive. Get this, the hybrid method actually gave more accurate answers than trying to run the traditional calculations on the whole molecule. So by breaking the problem down, they not only made it easier to solve, they actually got a better result. How cool is that? Okay, next up, they took on an even more practical challenge, cyclohexane. This molecule can twist itself into several different shapes, or conformers, and the energy differences between them are incredibly tiny. Getting this right is a massive test for any simulation method. You got the really stable chair shape, then the less stable boat and twist boat, and the very high energy half chair. This is such a delicate test because those energy differences are minuscule, and being able to correctly rank their stability is the mark of a truly accurate method. So, how did the new method do? It passed with flying colors. It correctly ordered all the conformations from most stable to least stable, perfectly matching the gold standard reference calculation. It absolutely nailed that delicate energy landscape. All right, let's zoom out for a second and look at what this successful test run really means for the bigger picture. Because this is more than just one cool result, it's pointing toward a whole new way of computing. What we're really seeing here isn't just one new algorithm. It's an early demonstration of a whole new model, something called quantum-centric supercomputing, a future where quantum and classical computers work together, hand in glove, each one playing to its own unique strengths. So why does this matter so much? Well, for one, it means we don't have to wait for some perfect, fault-tolerant quantum computer in the distant future. This approach lets us get real, valuable work out of the noisy near-term quantum devices we have right now by teaming them up with our powerful classical supercomputers. This creates a real, tangible path to accurately simulating the truly large molecules, like proteins, that are so central to drug discovery. By breaking down what was once an impossibly large problem into a series of manageable, collaborative tasks, this work provides a real path forward. It turns what we called a grand challenge into a grand opportunity, one that could potentially accelerate the design of new materials and, yes, new life-saving medicines. This quantum shortcut might just be the direct route we've all been looking for.